usual, I thought I was done. I have just a few more comments to make about what I was doing last time. I think that the most wishy-washy part of the proof I gave was the claim about untangling moving cusps down and untangling the one handles, right? So we had some situation, this maybe, and you wanted to, could you get from these a 1 and 2, 1 and 2, and could you get, you wanted maybe there was a handle slide here, for example, in those two one handles, and you wanted to be able to go from there to something like this, maybe, and then you want to be able to go from there to, and then you want to be able to pull this this one handle below. I mean, if you can do moves like that, then you can sort of keep going, then if you needed to pop this one inside. But, to be able to untangle everything and get rid of handle slides, of course there might have been a handle slide here, so then you couldn't do it. In that case, you have the problem there. So I think I think I've been pretty careful about why, if there is a handle slide in here, then you can't separate these, and why if there isn't a handle slide, then you can. And it's really sort of, I had two claims. One was that first is that you can drop a little cusp like that down below, and then there are two choices how to do it, and that, so basically I'm saying anytime you have a good way to say it is, this birth is happening at a point in the manifold at this time. Remember, that's always time in this direction. Right? So in your manifold, that birth is happening at a fixed point, and if you can find a downward flow line, I mean, there is a downward flow line passing through that point, or you don't even need a flow line if you can just find a path in the manifold that's decreasing with respect to the Morse function, then I claim you can drop that birth so it happens. The better thing to say is that I sort of have this, and then I do a very steep drop, so it's going to be birth happens right down, something like that. Draw it steep enough. But anyway, you want to say that there's a way to drop that birth arbitrarily low as long as you can find a particular path from that point going down from the manifold. And so once so you do it sort of you do it instead of moving it to the left and down, you just move it sort of straight down. Of course, you have to do everything so that it matches up with what happened before and after. There are two ways to. So before I talk about what's with the hand slide, just talk briefly about that. I'm not going to construct a full argument. There are two ways you might think about constructing the full argument. One is slightly nicer in a big picture than the other. So one way you might do it is just sort of I think it's like a surgery type argument in the sense of I'm going to take something out and put something back in. Here's a particular one-parameter family of Morse functions. I'm going to construct out of the blue a new one-parameter family of Morse functions that is exactly equal to what I had to the left and what I had to the right, and then I'm going to just plug in something new here. Right? It's going to be the same manifold and so on. It's just going to be different one-parameter family of Morse functions. The other way, which is nicer, is to actually construct a homotopy from this homotopy to this homotopy. So in other words, rather than just cut something out and put it in a discrete operation, show a way to continuously deform this one-parameter family to this one-parameter family. The reason why the surgery type argument might be a little easier is that you could then use what we know about one-parameter families as being broken up into handle slides and so on, and say it's sort of you can sort of try to discretize the whole operation. Say, okay, a Morse function is really a handle decomposition. Well, with a little bit more, right? Because you need to know which handles were attached first and second. So then you say there's a handle decomposition just to the left. So I'm going to forget about. In order to understand what's happening at this slice, I'm going to say I'm just going to remember the handle decomposition here. I could call it an ordered handle decomposition. And then I'm going to remember the ordered handle decomposition here. I know exactly what they are. I know what a birth does to a handle decomposition. This handle decomposition changes into that one by adding exactly a canceling 1 and 2 pair of one handle and a two handle, and then I'm going to and then there's the ordering, and I'm going to say, well, I could just as happily attach that canceling pair lower than this one handle as long as I have that arc down there. And well, I could just as happily attach it first, and then I know that I can pull, so you sort of would construct something where you have the birth happening below this one handle, so here's the 1 and 1 and 2, and then you say, I know that because this is happening in a ball, I make this happen in a ball, which is disjoint from this, I can therefore drop that one handle below. That picture is really the same as this picture, right? Dropping below, and therefore I have the same handle decomposition at the right, and therefore I can plug it in and I can continue. So that sort of argument, that's the discrete argument. Discretize everything, then do it in steps. And that's sort of a little more appealing as a technique of proof, but at the same time you might like to, sort of obvious, but you might like to really nail it down, that this one parameter family is homotopic to that one parameter family by the obvious homotopy, which just drops it down. And to do that construction, it's a little more fiddly because what you really want to say that you're going to do something in a neighborhood of a particular descending path. You need to write down sort of local coordinates for everything happening there, which is not that hard. Then you need to use a carefully constructed bump function to sort of in time modify the one homotopy to another. And as always with bump functions, as I pointed out with the one mistake I made earlier, you always have to be careful you don't introduce new critical points when you just push things down careful. So I won't do that, but that's how you would construct such an argument. This is definitely done in Cerf's original papers, and his moon is named something. Now the other thing is, what about the issue of the handle slides? There it's easier for me to see it from this discrete point of view. And I think what I would do is, if you want this handle slide not to be here, the first thing I would do is you can argue, again, just sort of the easiest thing is to make the handle decomposition type argument. You can say, well, this handle slide could happen, arbitrarily close to this birth. So then you want to draw a picture of what's happening with, suppose there's a birth immediately followed by a handle slide. So now you want to say, I've got my particular, and I'll draw a three-dimensional picture to illustrate. So this is the one handle that already exists, all this A. And now I'm going to have a one handle with a canceling two handle B. And they're just born somewhere. So they're born sort of small, and they're somewhere in your manifold you've got a small one handle born and the canceling two handle that goes over. Okay. And then immediately after that, this thing slides over there. Right? So then right away, so followed by that, immediately after that, this thing slides over. One handle, and then you get the second one handle now is going to look like right here somehow. But this is harder to draw, but the two handle, notice that the two handle is going to go up and over and back. See what right? When you drag the foot of this one handle up and over, you've got to drag the two handle with it. Okay, I might not look exactly like that. Anyway, that's right. Anyway, you can also imagine that it's sort of just you've got some membrane coming down here, and you've got something to drag this over, and the membrane ends up going with it. So now you want to say, well, how can I want to so I want to now say that I could make this birth happen, quote unquote, after the handle slide. And another way to say that is I want to just arrange that when it's born just exactly like that. It's born already slid in a sense, right? So that I want to arrange so that it's born and looks like that. So there isn't a handle slide because it was born having already slid, but that's fine too, because when a one handle, I guess the best way to visualize how that birth would happen is you have here's your one handle A that already sits there. This was A, this one B is C, This is on 1 half of A now. And then, remember, here, this is happening above the 2n, right? So you can just have the, well, the point really is that, so there's a level set above all this stuff, and you could just happily have the birth of the 1-2 pair happen, say, right there, for example. But that's really the same thing is happening down. So it's so that the two feet come down the two sides. But that's really no different than having it happen, the birth happen right there, and just as soon as it's born, it looks like that. So I don't know if that's very convincing, but there's something, you know, it's an interesting question. When a 1 handle is born, right? Where does the 2 handle go? And it can go around any curve, and it doesn't sort of matter that, you know, I've said it's small, but what does small mean in this context? So it can happily have just been born like that. That's really all I'm saying. And so if it's born like that, then yeah, I guess what is confusing about this argument is if that's true, how can the 2 handle? Let me not say any more about that. It doesn't confuse it. But that's the idea that somehow can be you can this picture of sliding they'll making the slide happen. You know, so you can slide this. You can move the handle slide off the end of the cuts by making it happen. That's all it is. Let me give you. I'm about to. That's all I want to say about that argument. Unless I think of some clarifications another day, I want to start actually doing filling in gaps for things we've missed. In particular, I want to start with the Morse lemma, which is sort of have, of course, the Morse theory without proving that Morse functions have standard forms. So I want to get back to that. But let me give you a extra homework assignment, which I hope is not arduous. And I think I want this to be a written homework assignment. Okay? And the written homework assignment is for you to submit a list of a few points which, let me say it this way, where I have either not given proofs at all or not provided sufficient detail. In other words, things that well, I mean, it could be things where, just to remind me, by the way, you promised me a proof on this, right? Or something where I bullied you or just sort of said, okay, we're done, and you really don't get it, and would really like to see some more clarification, okay? And either of those things. I mean, it may be something where you're happy to buy it, but you just want to remind me that it's something important that we haven't done, and you know, what are all the little pieces. So I want you to take a little time to take stock of what we've done. We know we've had a big application now, and take a little stock of that and think about, well, what are the pieces? I mean, the big thing is existence of Morse functions, and I'm going to start doing it. So you don't need to give that. I'm about to do that, okay? But there's, especially with regard to gradient-like vector fields and so on, there's a lot of fiddly things. So help me think and help you think about, you know, the missing details. Anyone following this online can email me such things, like Bruce. Okay, so my goal now is to prove Morse lemma. And so the Morse lemma, I'm still deferring the part that Morse functions exist, actually, but that's coming later soon. But the Morse lemma says that if P in M is a critical point of function f and R, and in some local coordinates, the matrix of partial derivatives, the Hessian of f, and 0. Actually, let me already call it Q. So Q, let's see, Q sub 0, which is the matrix of second partial derivatives of f 0. If that matrix is non-degenerate, so think of it as a symmetric bilinear form. Therefore, I just ask you this determinant of 0. Then there exists some other coordinates such that f, with respect to which f equals, sum of the plus or minus x squares. So I'm gonna now that's what we're gonna prove. I'm gonna state the same. I'm gonna state the same theorem again, slightly fancier way. So another way to say this is let's let Q sub 0. Actually, maybe I don't want to call it Q sub 0. Maybe I want to call this. I want to think of this as a matrix, just a matrix of numbers. Okay, so I'll call this the matrix little qij. The qij of 0. So little qij of x, little qij of something is going to be just the part of the ij partial derivative. Okay. So I'm going to define a matrix, a function q sub 0 of x, which is the sum over all ij of q sub ij at 0 times xi xj. Okay, so that's the actual bilinear. That's a degree 2 polynomial bilinear form coming from this 2 by 2 matrix. Right? You can also think of this as, so equivalently, this equals x transpose qij. Right? So one of the equivalent statement is that the conclusion of the theorem is that there exists some local coordinates in which f of x just equals q0 of x. So that's that's an equivalent statement. So why is this an equivalent statement to this? Well, the point is that that may seem weaker than this because saying it's sum of plus or minus xi squared it seems like much stronger than saying it's just equal to that particular quadratic form. But there's also the classification of quadratic forms. So the connection between these two is a linear algebra effect, classification of non-degenerate quadratic forms, which says that any non-degenerate quadratic forms, any non-degenerate quadratic form is up to a linear, is isomorphic by a linear change of coordinates on Rn to a sum of squares. Okay, and it's a diagonalization argument. So that's linear, pseudo diagonalize. It's the kind of diagonalization where you change basis by, you do row and column operations. So you're changing by, putting a matrix, elementary matrix on the right, and its transpose on the left. And by those operations, you can transform any non-degenerate quadratic form to a quadratic form with just plus or minus 1s on the diagonal. So that I'm going to assume here, and not prove that. But once you have that, then the point is, if f of x is q0 of x, then you can change it by a linear change of coordinates to something plus or minus 6x squared. So this is what I'm really gonna, this is the way I'm really gonna prove it. And by the way, the proof there, you know, zillions of Morse lemma is one of those, such a standard thing. There are lots of proofs out there. The proof I'm gonna follow is the proof I'm gonna follow is from by Martinet on singularities of differentiable mappings. And I like it because it kind of feeds into a bunch of other ideas. Okay, so the first thing we're going to do is remember that. So step one is going to say that f of x can be written as the sum of some function q sub ij of x times xi xj. Now, I actually might have misled you. Q sub ij of x is not going to be the matrix of partial derivatives with respect to at a value x. So q sub ij of 0 is going to equal to that, but q sub ij of x is going to be possibly some different function. Okay? So, you know, this is just some such that q sub ij of x is equal to q sub ij of 0 is equal to partial square root with respect to xi xj at 0. But if I'm at some other point, I'm not necessarily equal to these exact partial derivatives. This is, so where does this come? I mean, this is really Taylor's theorem. There's just, all this is saying is there's some function. Because of the fact that it's a critical point, right? Therefore, you know, if you write down the Taylor polynomial with a remainder, right? Or, because we don't necessarily need to know the Taylor series conversion. You write down Taylor polynomial with a remainder, you know, you get f of 0 plus something involving first derivatives, plus something involving, you know, times x's, plus something involving second derivatives times xi xj's, etc. Right? But if the f of, I'm going to assume f of p equals 0, right? This will be easy. So we don't have that, and then we don't have a, this is an ij. We don't have a first order term, and we're just left with that. But let me just, I mean that, you know, maybe that's completely standard analysis to you, but just for me, since my analysis is rusty, let me just review why this is true. The claim is just there is some function satisfying this property, even without the non-degeneracy, just the fact that the first and second derivatives are 0. And so, you know, why is this true? So this is true because, you just do it once. I mean, I'm really just going to go through the proof of, in some sense, the proof of Taylor's theorem with an rangeable remainder. So first of all, you know, point 1 is you can write f of x as, you know, the sum of, you know, you just do it one step at a time. So I write f of x as the sum of some hi of x times xi for each variable. And how do you get those h sub i's of x? You know, you get the, you know, what are you doing? You're really saying, where does this come from? This comes from the fact of saying f of x is really the integral from 0 to x of df, right? Okay. I'll just do it in one variable, and then it's saying, you know, f prime of x, f prime of u du, something like that. And the same thing works in many variables, and then you want to reparameterize that as 0 to 1, so you make some change of variables like u equals lambda, u equals lambda x, right? And then this becomes the integral from 0 to 1 of f prime of lambda is the variable, right? Lambda is going to go, when lambda goes from 0 to 1, u goes from 0 to x, so this becomes f prime of lambda x. Since lambda is the variable, x is sort of behaving like a constant, so you get, you know, du is x d lambda, and if you're doing this in many variables, this would be, you know, this is split up appropriately, right? And then the point is that it doesn't, you know, this is just x times, there's your function, interval from 0 to 1, f prime of lambda x d lambda, and that's your h of x. And when you figure out what's h of 0, well, so that's smooth by integrate theorems by integrate how integrals and derivatives relate to each other, and then h of 0 is the integral from 0 to 1 of that prime at 0 d lambda, which so that's a constant, so that's just f prime at 0. And if you do things in several variables, the same thing happens. And so in particular, this h, so in several variables, h sub I of x ends up being partial of f with respect to xi at 0. And then you repeat, you apply that same thing to each of those functions.
You mean h I of 0?
H I of 0, thank you. H I of x is then obtained by integrating. And you apply those again, so then do it again. I. Okay, and that's how you get each I you repeat, and that's how you get the second derivatives. Okay, once you get that, then all right. So now I want to show that f is so we have this thing. Let me call this function okay, so what you want to think now is that this, so f of x you can think of as a I'll write something that looks kind of funny. So step 2 is we're going to write f's, let q sub x let q sub x be the quadratic form q sub x of, well, I need another variable, right? So I want to think q sub x is the quadratic form q sub x of u or something equals the sum q sub I j of x ui uj. Okay, so what the point is, I want to think that there's a quadratic form that is varying with where I am. So f of x, at each point, f of x is obtained by taking some quadratic form and evaluating it in terms of at the xi's and xj's. So, this is sort of a weird way. So now I'm going to say f of x is q sub x of x. Okay, so just formally, that's what I'm doing. What I'm doing is I'm saying that these q sub ij's of x is packaged together as a quadratic form. At each point, that gives you a quadratic form, and so I know that q sub 0, the quadratic form q sub 0 of x, is precisely the is what I have here, right? So that is the partial squared f sum squared with respect to xi xj times xi xj. And so what I want to do is somehow see that this sort of change coordinates, so I see that this quadratic form is actually staying constant as a rather than it being I'm saying I evaluate a varying quadratic form at the point and see what I have. And I want to sort of change coordinates so that quadratic form is not varying. And the idea now is to say that there exists a for x close to 0. I mean, I've already in the local coordinate system, p is now 0, right? For x close to 0, I can write q sub x of u as really q sub 0 of h sub x of u, where h sub x is a linear transformation. Depending, varying, depending smoothly on x. So I have this quadratic form that's changing with where I am, and I'm saying that what this really is I've got the best way to think about what's going on here is I can take any quadratic form and I can precompose it with a linear automorphism of Rn, and I get a new quadratic form. So I can think of the linear automorphism as GLN of R acting on the space of quadratic forms. And so I'm really saying that if the important thing is that the orbits of key fact, so the orbits of non-degenerate quadratic forms under the action of GLN are open. So if you move a non-degenerate quadratic form a little bit, it stays in the same orbit. And actually, what are the orbits of non-degenerate quadratic forms? They're precisely given by the signature. They're plus or numbers of minuses. So the claim is that any two non-degenerate quadratic forms with the same number, that are equivalent, any non-degenerate quadratic form is equivalent to that sum of plus or minus xi squareds, and if they have the same, if they're equivalent to the ones with the same number of minuses, then there's a linear transformation taking one or the other, and so you can see this by figuring out that this non-degeneracy condition is really an open condition. Right? The idea is you wiggle something a little bit, it's going to stay non-degenerate, and this index, which distinguishes the orbits, is something discrete. So there's no way in a small perturbation you're going to jump from some index to some different index. That's the idea. And so once you do that, then you know that if you're changing, if you're moving around, if you're changing the quadratic form a little bit, you're just moving around in the same orbit, and therefore you can achieve that moving around in the same orbit by actually changing by a linear automorphism Rn. And then we are almost done because let's see. Now it's just a matter of putting all the stuff together. So now I'll write something again that looks kind of funny, which I'll write. So f of x, maybe the one thing that I haven't explained to you is how you know that you can prove that it depends smoothly on x. And really sort of locally, when you, there's actually something to say here about group actions and so on. You can sort of think locally, you start at this fixed quadratic form Q0, and you start moving it around by h sub 0 is the identity, right? You start moving it around by different elements of GLN that are close to the identity, and you'll stay in the same orbit. And you want then to know that, the dimension of GLN is probably bigger than the dimension of the space of this quadratic form. So you probably, some automorphisms will preserve, that will not change your quadratic form at all. So you want to say that so you've got GLN acting on the space of quadratic forms, you've got a fixed quadratic form, you're interested in its orbit. What you really need to know is that there's a particular, the space of quadratic forms you're looking at is k-dimensional, GLN is, L-dimensional. You want to know that through the identity there's a k-dimensional, locally a k-dimensional submanifold that achieves all the different variation you might want to achieve in your space of quadratic forms. In other words, that's transverse to the stabilizer of that particular quadratic form. You've got a particular quadratic form, you've got a stabilizer, which is all those elements of GLN that fix it, and you want to pick transverse to it a smooth submanifold that will allow you to move in all the different directions you might move smoothly. And then you can argue then here you have sort of a parametrized family of quadratic forms close to a particular one, and so that's there's some smooth manifold worth of quadratic forms there, and you can therefore find a smooth submanifold with the space of inside GLN corresponding to that. That's there's a formal way to say all of that in terms of Lie group actions on manifolds and stabilizers and slices, and there's probably some theorem about group actions underlying all of that. I'm not saying very well, but maybe intuition is pretty much right. So then, f of x is, well, we already have it, it's q sub x of x. So it's this quadratic form where you plug in the same value of x at each point, and then we just write that here, that's q sub 0 of h sub x of x. So this is again finding at any point we have a linear transformation, and then we're applying that linear transformation to the point, right? And finally, we want to say that let's let phi from some open neighborhood of, let's say, just phi is equal, it's phi of x equal h of x of x. And we claim that this is a phi of 0, 0, right? Because h sub 0 is 0, h sub 0 would be identity, so it's 0. So phi is a diffeomorphism. I'm going to write phi goes from Rn to Rn. It's a smooth map from Rn to Rn. Really, actually, it's probably open neighborhood. Everything's only defined open neighborhoods of origin, but I'll just say that. And the claim is that this is locally diffeomorphism. And the way to see that it's locally a diffeomorphism is actually just to see that how do I want to say that? The point is that
Isn't h of x of u?
H sub x of u is a linear isomorphism. Okay.
So like, isn't
but,
this is just the,
I mean, so suppose for example, why would it fail to be a diffeomorphism? Suppose it happened that suppose we're in R2, right? Okay. At this point, we have at the origin we have the identity, right? Suppose it happened that at some point on the y-axis we have a suppose h sub 0 epsilon was rotation by 90 degrees, and everything on the y-axis would go to the x-axis, right? And suppose h sub epsilon 0 was the identity, then everything on the x-axis would go to the x-axis. Then I'm supposed to say h sub 0 epsilon of 0 epsilon, and that's going to smack the y-axis down onto the x-axis. H sub epsilon 0 of epsilon 0 would keep it at epsilon 0, and so 0 epsilon and epsilon 0 would both go to the same point. But that's not going to happen because this one parameter family of linear automorphisms of Rn, one parameter family in GLN, it's not going to, it can't, the point is it starts at the identity. So when you move a little bit in this direction, you can't suddenly become rotation. You can't suddenly be the map that sends everything to the x-axis. So it's a little more subtle than just saying it's, because it's linear here, that's fine. you can figure out that really what all you have to do is compute the derivative of this function at the origin, and it actually ends up, I think, equaling h0. It's, now I'm suddenly confused. I had to sort it out 30 minutes ago, I don't know, an hour ago. And it's not, I mean, it's somehow this argument I just gave here is the key idea. But I'll see if I can. So it's exercise, or maybe I'll clarify next time. I thought I knew that well enough. I didn't need to write it down. But here's 1, 0. I mean, somehow, as you move infinitesimally in some direction, you stay very close to the identity. Therefore, the actual value at that point has moved infinitesimally in that same direction. Right? That's the right idea. And so, modulo that, we're done. And that proves the Morse law. And I wanted to say it in terms of sort of emphasizing that, there's two parts to it. There's like classification of quadratic forms, and then showing that everything is equivalent to the quadratic, to that given quadratic form at the origin. So the next thing then to work towards, which I won't finish today, is showing that. So the next thing is to show that Morse law is generic. Suitable sense. And the first thing that I'm going to do is show that this condition on the Hessian is actually a kind of transversality condition, right? And if you believe it's a kind of transversality condition, that should help at least work. Although it won't be that won't immediately imply that it's generic, but it will be a step in the right direction. So non-degeneracy. So what kind of transversality can it possibly be? The transversality it is you start with f from m to r, and that gives you df. And df is a one form, right? And so df is a function from tangent space of m to r. You can think of it that way. Or you can think of this df as a function from m to the cotangent button. And thought of that way, we want to say that you can actually think of the graph of df as sitting inside it's the cotangent bundle. That's so. The claim is that this non-degeneracy is equivalent to. So this is a section of. It's a section because dfp is in tp star m, the fiber over that point. And so we have this schematic picture that here's M, here's the fibers of the cotangent bundle. And so M sits inside T star M. We can call it the zero section if you like. Zero sub M or something. Zero section. And the claim is this is the df of p at every point. We have something in that it's that df is transverse to zero section. So that's the claim right there. If we unravel what it means for this one form to meet the zero section transversely, we will recover the condition of the non-degeneracy condition. So to do that, we have to give ourselves some this should just be a local property. So again, well, so the first point is the places of intersection between df and zero section are just places where df equals 0, which are critical points, right? So these are critical points, but we don't want to have something like that happen instead. So choose at critical point P. We're going to choose, what I want to do is I want to think about this manifold M, and I need coordinates, I have T star M, and I need coordinates on it in which to think about transversality. So we choose coordinates. X1 xn on the manifold M. Okay, I guess I was calling X anyway, the manifold M. But that's just on M, and how do I get the corresponding coordinates on T star M? I'm going to, what shall I call them? Okay, and then let U1 up to UN be the corresponding coordinates. Well, on TP star M, for any P in this, TQ or whatever, for any Q in this coordinate neighborhood. So what are the corresponding coordinates? So the point is, for any function g from M to R, we have dg in local coordinates can be written as the sum of dg at a point q can be written as the sum of the dx I at q times some function, some numbers, some coefficients, right? And those coefficients are going to be those are going to be i's of q. Times, I'm just going to write it times some numbers in ui. That's being sloppy because what I should really have, I mean, you want to be very careful about it. UI should be a function from, so the better way to say it is, actually, the better way to say it is, if I have a cotangent vector, so if V is in TQ star M, okay, V is at a point Q, right? Then I'm going to tell you what all these four coefficients, all these two and coordinates are, then xi of the vector v at the point q is just xi of q. That's just forgetting the vector part, just like where you are in the manifold. And then ui, and then if I write vq as the sum of, say, ai times dxi at q, then ui of the vector vq is this number ai. So they're just the coordinates that pick up the coefficients with respect to this type of things. So you don't have to do all that, but it's worth spelling out. Okay. So now we want to, so given, well, we're out of time, so I'll tell you what we're doing next. What we're really going to do is see that we're going to, one thing that's I remember always being confused about in multivariate calculus is the second derivatives, that's a 2x2 n by n matrix. It ought to be a map from Rn to Rn, where it would, but it's not, it's a second derivative, right? Where is it a linear map? And how is it a linear map from anything? And we're going to see that actually, if this direction is n-dimensional, this direction is n-dimensional, this, if you think of it as a map from, anyway, the tangent space to this section, df, is going to be precisely the graph of that Hessian, that matrix of partial derivatives, second partial derivatives, as a map from the x1 up to xn space to the u1 up to un space. And so knowing the non-degeneracy of it is going to correspond precisely to that transfer